All right, apologies if there's a little bit of background noise today, but I'm going to record for you a little video about tree diagrams, which you sometimes hear referred to as probability trees or probability tree diagrams, all referring just to the same thing. And the whole point of a tree diagram is that they can be useful when you're dealing with more complex probability questions, right? Sometimes you are able to solve the problem in a way where you won't need a tree diagram. The question's simple enough. In this question here, we have Bubbins, it's his birthday, and his mom says, "All right, you can reach into the cash jar because I forgot to get you a gift, and randomly take out two bills. You got to close your eyes first." So Bubbins, his eyes are closed when he's reaching in there. The jar's got four $5 bills, two $10 bills, and three $20 bills. And if the question is just something like, what is the probability that he ends up taking two $20 bills out of the jar, then we're all right for a question like that, right? We use our basic concepts. We know, okay, find out how many total possible outcomes are there. Well, if at the start we got four four $5 bills, two $10 bills, and three $20 bills, that's a total of 9 bills in the jar. Right? That's our total possible outcomes for that first step, and 3 of them are $20 bills. So if we want to know the probability of getting a $20 bill on the first draw, that's just 3 out of 9, right? Favorable over total. That's our basic probability. And since it's without replacement, that means that if we've taken a $20 bill out on our first step, then there's only 2 left in the second step out of a possibility of 8 bills, right? Our 3 over 9 becomes 2 over 8 for that second step because it's dependent probability, it's without replacement. And then we take our 2 steps and we multiply them together. That's what you do. You multiply when you have 2 steps. 3 over 9 times 2 over 8, top times top, bottom times bottom, you get 6 over 72, which you reduce to 1 over 12. That's the probability that he gets two $20 bills out of that jar. Not very high, but there's always a chance for good old Bubbins. But sometimes you can have a question where the probability involved maybe isn't so straightforward, and you might want to have something like a tree diagram as a tool available to you. Let me give you an example. Same scenario with Bubbins, except the probability we want to calculate isn't that he ends up with exactly two $20 bills when he reaches and takes 2 out of the jar. Instead, we want to find out what is the probability that Bubbins ends up taking a total of at least $20 out of the cash jar. Now, if you look at this real quick, you may not necessarily see how this is a more complicated question, but it's because when you're trying to figure out favorable over total, the favorable outcome in that first step isn't so clear, right? Because you're trying to end up with at least $20, which means you could get a 5 and a 20, or a 10 and a 20, or a 20 and a 20, or a 20 and a 5, or a 10 and a 20. I already mentioned that. It's easy to lose track of all these outcomes. But what's favorable and what's not favorable isn't obvious for each step, right? A $5 bill on the first step might be favorable if you end up getting a 20 on the second step, because that ends up being an outcome that works for you. But if you're going to get another $5 bill on the second step, then it wasn't favorable. So it starts to get a lot more confusing. That's why you want to have a tool like a tree diagram. We actually won't solve this particular question today. We'll leave that for another day. But I want to set the foundation of how you can use a tree diagram to keep track of all your outcomes. And there's a few things I want you to remember right at the start about tree diagrams, because they're the things that people have the most difficulty with when they're getting used to making them, is that each split of branches, you'll see what that means in a picture in a second, each split of branches is between outcomes of a single step. Okay, so that means, like, let's say, for example, I'm talking about a step where I'm flipping a coin. The coin could end up being heads or tails, so that split of branches goes one to one of the outcomes, heads, and the other to another, which is tails, right? I wouldn't split it up, and like if this is a 2-step experiment where I have flipping a coin and then rolling a die, the split of branches here isn't flipping the coin for heads is and then rolling a die where tails is. Instead, heads and tails, the 2 outcomes from the step, are showing up as a split. The next thing that people have the most difficulty with is remembering that each step in the experiment shows up in a column. So if you're starting out, as you'll see, we start out with this omega symbol as our starting point. The first step in your experiment is going to show up here. So let's say I'm talking about a 3-step experiment where I have a coin flip and I'm rolling a die and then I'm spinning a spinner. The coin flip is going to show up in this column here. And then the next step in the experiment is going to show up in this column here. Finally, the 3rd step in the experiment shows up in a separate column here. Now, this is going to be a lot easier to understand if we do an example. So let's say we have this one. Horace the ox will eat some hay, and then he's going to have some slop. It's a great day for Horace. He loves hay, he loves slop. Fantastic. Maybe it's his birthday as well. The hay he will eat may be yellow, beige, or pale. And the slop that he'll eat may be sour or bitter, right? And Horus is kind of a random ox. He doesn't really choose. He just kind of, whatever food is in front of him, he goes for it. So let's set up a tree diagram showing all the possibilities, all the branches that could describe Horus's situation. We always start off, you'll see here, we start off with this symbol here. And it kind of looks like an O that doesn't quite finish at the bottom. It's got little feet, right? It means everything. It's a Greek letter. It comes at the end of the Greek alphabet, and it represents everything. Like the way you'd say from the beginning to the end. In Greek, you'd say from the alpha to the omega, right? So omega just means everything. We use it as kind of the root of our probability tree to show that all possibilities that could happen are ultimately connected back to this one. So that's just a symbolic way of saying we're starting from here. Then once you've got that symbol written down, next thing you do is you grow some branches out of it for the first step in the experiment. And remember, we put each step in a column. You wouldn't draw in these lines for the column. This is just to help you out because this is you getting to learn tree diagrams. So the first step in this experiment for Horus is him eating the hay. So we want to include the eating in the hay, all the possibilities for eating in the hay in this first column. And we saw that he can either be eating yellow hay, beige hay, or pale hay. So I have each of these three possibilities for what could happen in that first step of the experiment are showing up in this column here. They're branching out from the beginning. These are all outcomes from that first step. I'm not branching it to say something like, okay, this is eating hay up here and this is eating slop down here. No, all this whole column is just about that first step is just about eating the hay. So I split it off into the three possibilities here. And now I say, okay, the second step is him eating the slop, right? That's going to show up in this other column here. The second step, each of these possibilities, like if he eats yellow hay, he might from there end up subsequently eating the sour slop or the bitter slop. If he eats the beige hay, again, that also has two possibilities. They're the same two possibilities that we're showing up here. So that makes sense, right? If he eats the beige hay, he might end up with sour slop. He might end up with bitter slop. If he eats the pale hay, he might end up with sour slop. He might end up with bitter slop. So I've got two steps in this experiment, the hay that he's eating and the slop that he's eating. The first step, the hay eating, shows up in this column. Second step, the slop eating, shows up in this column. So that's essentially how a tree diagram works, except at the end, what you do, and this is kind of, you'll see when we use it for calculations, what the benefit of it is, at the end of each branch, you know that this corresponds to one combination of outcomes for the experiment, right? This one here, we see that's yellow hay and then sour slop. So that means that in this, at the end of my second step, I'm going to put all these outcomes afterwards. This is yellow and then sour, so I'm saying this is the outcome yellow, comma, sour. Notice I've got parentheses around here to indicate that this together is one outcome. It's not a list of two different outcomes, it's one combined outcome. Here, if I've got yellow hay and then bitter slop, by the time I get to this branch, I know this represents yellow, then bitter. Then beige and sour shows up as this outcome, beige and sour, beige then bitter, pale then sour, pale then bitter. You get the idea. So I see here I end up having 6 outcomes at the end, which based on the math you've previously been doing about figuring the basic counting principle, total number of outcomes, 3 times 2, right? There were 3 possibilities here, yellow, beige, or pale. 2 possibilities here, sour or bitter. 3 times 2 gives me 6. That's why I end up with 6 listed here as the outcomes. Now, a reminder of the things that people tend to forget, or they tend to have the most trouble with in getting used to this, and that you'll need practice in overcoming, there is this one, that each split of branches is between outcomes of a single step. We already said this. When your branches split off, you're not splitting off into hay and then slop, right? You'd have all the possibilities for hay as branches coming out of the beginning. In this case, if I'm flipping a coin, I have all the possibilities for the result of flipping the coin is growing out of these branches here. The next thing is that as you're moving along in the tree diagram, once you're building layers, each step in the experiment shows up in a column. So if I have a coin flip, and then a die roll, and then a spinning of a spinner, each of those is showing up as a set of branches, as a generation, you could think of them as branches going left to right across, right? The first step here would be coin flip, then I'd have some branches for the rolling of the die, then I'd have some more branches out of each of those branches to represent the spinning the spinner. That's your essential tree diagram knowledge. Best way to understand how to do this is with some examples. So you'll see there's some examples lined up for you to do. And if you have any trouble with those, then please, by all means, let me know so I can help you through.